Welcome to a tutorial of Proflan YouTube channel. In this particular video, we're going to look at the concept of capacitors and capacitance. Capacitors are devices which have the ability to store charge. And if you're asked to define the term capacitance, we're going to say capacitance of parallel plates is the ratio between the charge stored in one of the plates divided by the potential difference between the two plates, that is set between the two plates. So in this particular case, we're going to look at some of the questions that have been asked in various questions so that you can be able to see how to approach them. So in front of me, I'm having here different the notes on this particular topic, which you can be able to access in our Patreon page. So when capacitors are connected in parallel, you need to understand that the total capacitance is gotten by finding the sum of the capacitors, the individual capacitors. But when capacitors are connected in series, you are going to get the total capacitance by one of the capacitor plus in that order, so that you can be able to get the reciprocal of that. You need to understand that capacitors, they are usually in the reverse of what we were doing in resistors. So with me here, I have the worksheet which we are going to look at, and this is the worksheet on A-Level Physics Cambridge 9702, different questions that have been asked the previous years. So we are going to look at how you're going to figure the question out. One of the questions that you can see that was asked here is the question of defining capacitance, and I've demarcated that. I've shown that in our notes that if you are asked to define capacitance, this is exactly what you are going to say. You are going to say that capacitance of parallel plate capacitors, let me just move this up. Just check the capacitors there. Yeah, this is the section that I'm talking about. The capacitance of parallel plate capacitors is the ratio, is defined as the ratio of the charge stored on one of the plates to the potential difference between the plates. That is exactly what you're going to say there, so that you can be able to earn those particular marks. Yeah. So you are supposed to mention is a ratio between the charge in one of the plates to the potential difference between the plates. And if you do that, you are going to earn your marks, and the marks will be awarded here will be 2 marks, because when you're talking about charge stored in one of the plates and the potential difference between the plates is going to earn you the 2 marks. Initially, uncharged capacitor X of capacitance C is gradually charged, so that the final potential difference between the plates is going to be V, and the final charge is Q. Now we are supposed to determine the expression. We are supposed to determine the expression for the work done on capacitor X during the charging process. So here we need to remember that work done is equivalent to the area under this particular graph. If you work out the area of this particular graph, is going to be, it is going to give you the work done to charge this particular capacitor. Remember, for you to ensure that you force the electrons to be in one side, then some work has to be done. Yeah, if you are forcing electrons to be in one of the plates, work has to be done. So that is why we're saying the work done is equivalent to the area under a charge against potential difference. And if you work it out, you are going to get your answer as charge is equals to QV, because the height, this is a triangle, so it's gonna take area of a triangle formula. Then we have the next part, but something that we really ought to remember in this particular question, we are told that another capacitor Y is initially uncharged. The fully charged capacitor X is now connected to capacitor Y. You can see now these two are in parallel. So if they are in parallel, if they are in parallel, it means that the potential difference that is going to run when they are fully, because charge will move from X to Y, and then when it's fully charged, the potential difference are going to balance in that case. So the first thing that we need to remember, that when capacitor X, capacitance C initially at a potential difference V is connected to Y, the charge distribution is going to take place until both capacitors have the same potential difference. Charge is conserved. So meaning that total charge is going to be Q, because if this is charged, fully charged, is going to have a charge of Q. And then the combined capacitance, so let me just write here the combined capacitance. Capacitance total, because they are in parallel, is going to be C, that's the capacitance of X, plus the capacitance of Y, and that's the total capacitance is going to be 4. 4 is the total the total capacitance, and the final PD across the capacitor is going to be final PD across these capacitors is going to be, let me call it P final, is going to be the total charge. And remember the total charge that we are talking place about here, the total charge is going to be the total charge in Q, in X. So which means because the charge is going to flow from X to capacitor Y. So if X was having a total charge of Q, then it means that if we want to find the potential difference, we are going to say charge over capacitance, which is going to be equivalent to what? That is going to be equivalent to Q of the total capacitance. We have gotten it here, 4C, which is 4C, which is 4C here. Okay. Yeah. But we need to remember that capacitor C charge, remember charge is equals to CV, and the capacitor C was having a total charge of Q, but that charge is equivalent to the capacitance of C times the potential difference of C. Remember, it was fully charged. It was charged to a potential difference of V. So meaning this Q, we can replace it with CV over 4C. And this particular point, we can be able to cancel C and C. It will mean that the potential difference is going to be, final potential difference is going to be V over 4. That is the final potential difference. Find, so the final PD is going to be V over 4. So for X, the final PD is going to be V over 4, and also this one is going to be V over 4 because the potential difference is going to be the same in the two plates. Then we shall talk about the final charge. The final charge for X, how are we going to go about that? Final charge for X is going to be the capacitance of X times the potential difference of X. So which means, so charge for X final, let me just say final here, is going, remember charge is equals to CV. What is the final PD for X? Is this one. So this is going to be C times V over 4, and that's going to be CV over 4. So which means that the final charge is CV over 4, but CV is Q. So we are going to say CV is Q. This is going to be Q over 4. So this is Q over 4 at that point. But the capacitance for Y, so if we want to find the final charge in Y, we are going also to say, okay, right, the charge in Y is going to be calculated from the final PD for Y and the capacitance for Y, and that is going to be Q for Y final is going to be what? Is going to be charge is equal to CV, which is going to be the final PD for that one is also V over 4 times the capacitance of this is going to be at 3C, and that is going to translate to 3 over 4 CV, and that means it's 3 over 4Q. 3 over 4Q as the final charge for this particular part that we are having in this particular question. And if you are new to Prof Learn YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. All right, so moving on with this, we are going to look at the next question, and the next question is asking, I need to change this. I need to change this so that we can be able to proceed. The next question is asking us to state whether the total charge stored in the two capacitors is less than or the same as or greater than the energy initially stored in X. In fact, we are going to say there that the charge stored is basically, it's going to be less. It's going to be less than. It will be less than. Let me just write it clearly here. It will be less than. Is less than. And what's the reason as to why we are going to say it's less than? So why are we saying that the charge is going to be less than? Why? What is the reason? You can be able to do the calculations and then to show that, but we shall now answer the question why. Why is it less? Why is the energy less? Let me just get the answer from the comment section. I would like to read your answers. Why is the energy considered to be less in this particular case? So the total energy that is going to be stored after the connection is basically going to be less because during this charge distribution process, the energy is going to be dissipated, maybe in form of heat. Yeah, so energy is going to be lost, and that is why I'm saying at this given point that this is going to be, the energy is going to be less, because say, even though this question you were not supposed to indicate that, we can say now this is because some energy is dissipated in form of heat during charge transfer. Yeah, so during charge transfer, some of the energy is lost and some of the energy is wasted. All right, after looking at this question, let's move to the second question. And in this particular question, we are told to derive the expression in terms of Cex and Cy for the combined resistance of the capacitors in this circuit. So you can see here, these capacitors are connected in series and they are connected to a potential difference of V. So the first thing that you really ought to remember is that charge is equals to CV. You take the capacitance times the voltage, but voltage is charge over capacitance. Now, in order to derive this expression, there are a few things that we really need to put into consideration. All right, so in this particular question, we are supposed to derive an expression in terms of Cx and Cy for the combined resistance of this. These are two capacitors, guys. Two capacitors which are connected in series. Then what we need to remember is that if capacitors are connected in series, it means that the charge in this capacitor is equal to the charge. They are going to have the same charge. So I've written what you need to take note of. For capacitors in series, they have the same amount of charge in each capacitor. So in each capacitor, we're going to have the same amount of what? Charge. So if you have the charge Q, then you can be able to work out the potential difference, the voltage across that capacitor, by saying that charge divided by, because we know capacitance is CV, but voltage is charge over capacitance. So which means if we have the charge Q here, the PD for X is going to be Q over Cx. For Y is going to be Q over Cy. But this PD on this and this, if you add them, you get the total PD that was applied in the particular circuit. So that's why you can see I did that. And when I added that, something else you need to remember, this is the total voltage. And total voltage is going to be the total charge. The charge is Q divided by the total capacitance, which we can call C what? CT. So if you convert this voltage to charge over total capacitance, CT, then you are going to have this expression and Q cancelling out. You end up having this expression here, which means if you simplify that, we are going to have total capacitance is going to be Cx times Cy over Cx plus Cy. The next part is a section whereby we are told that two capacitors, P and Q, are connected in parallel to the power supply. Our voltage V. So the power supply was giving a total voltage of V. Okay. So which means that the capacitance P, we are told the capacitance of P is 200 microfarads, and the capacitance of Q can be varied from 0 to 400 microfarads. Then when Q is equal, CQ is equal to 0, Remember, these two capacitors are in parallel. So something that you need to remember is that the formula for capacitors which are in parallel is going to be given by the sum of the individual capacitors. Now, having two capacitors in parallel here, then one is having a capacitance of 0, then it will mean that we can continue and go ahead and say that the total capacitance is going to be remaining to 200, because 200 plus 0 will be that. So this is going to be our total capacitance. Energy stored in a capacitor is given by the formula a half times the capacitance times the potential difference squared. So our capacitance was this, and then the voltage is given as the voltage, the one that we are trying to show, because we were given the energy as 2.5 joules. So if you work it out, you are going to get exactly 5.0 volts as the potential difference between the plates. Calculate the total energy in joules stored in the capacitor when Q has a maximum value. What is the maximum value? The maximum value, we were told, is varied from 0 to 400. So if it's at the maximum value, then it means we can be able to say the total capacitance is going to be 400 plus 200 microfarad, which is going to translate to 600 microfarads. And then we can now be able to apply the formula for the total energy that is stored. So that is going to be 7.5 times 10 raised to the power negative 3, which is going to translate to 7.5. So those are the aspects that you have to put into consideration. Sketch the variation of the total energy is stored in the capacitor with Q, as Q is increased or is being varied from 0 to 400. So remember, we are talking about energy. Energy is equal to a half CV squared, where C is the capacitance, V is the voltage or the potential difference. So from here, we can see what's being varied is the capacitance. Yeah. So capacitance is directly proportional to the energy, because V squared is a constant. Yeah. Voltage is a constant. So since C is directly proportional, then it means we are going to have a straight line that is starting from 2.5 and it increases all the way to 7.5. Why is it starting from 2.5? It started from that point because when CQ was 0, the total energy stored was 2.5 millijoules. So when it was maximum, the total energy stored was what? 7.5. So that's why it becomes a straight line like that, guys. Let's look at this particular question. Also, we are told that 3 capacitors are connected as shown. We have 3 capacitors whereby these 2 are in parallel. So meaning the total capacitance for the parallel connection is going to be the sum, which is going to be 10 plus 20, which is going to translate to 30 microfarads. But now total capacitance for 2 capacitors which are in series, we are going to say is the product divided by the sum of the 2. Because these 2 combine to form a capacitance of 30, now we are going to have 2 capacitors. This is 45, and the effective capacitance of this connection here is going to be what? Is going to be 30 microfarads. So these 2 are in series to each other, then meanings we are going to work out the total like that, and that's going to translate to 18 microfarads. Part B. Capacitance of capacitance 45 microfarads is connected to the variable power supply, which is set to be 8.0 volts. The power output of this power supply increases so that the PD across the capacitor increases to 9.6. So we are supposed to calculate the increase of energy stored in the capacitor. Remember, energy stored is given by a half CV squared. Capacitance, we are given it. It's here, well seated there. But the voltage is increasing. So in that way, you are going to use the formula. Change in energy stored is going to be a half C times the change in the potential difference, which is going to be V squared 2 minus V squared 1. Don't subtract, then square. You square the voltage, then subtract. That's why you can see I said 1/2 times 45 times 10 raised to power negative 6 minus 9.6 squared minus 8.0 squared. So most of the students who will get this question wrong is that they will subtract the PD and then square. Remember, V squared is subtracted, so is squared, so you cannot subtract then square. So you do it like that. A sinusoidal AC power supply is connected to the input of the bridge rectifier, and then we are supposed to complete the circuit, which is going to smooth the PD. Remember, capacitors are also used in rectification to try to smoothen. Yes, because in rectification you may find that in the process, or maybe full wave rectification, you are going to have PD varying like that. So to prevent the PD from coming to zero, you need to connect a capacitor somewhere there, so that you're gonna have the PD smoothing like that, so that you reduce the ripples. Yeah, so since this was coming from the rectifier, then it means we're going to have our capacitor connected there, so that when the current flowing from here is going to charge the capacitor, when the PD falls to zero, then the capacitor starts to supply the voltage, so that we are going to have smooth ripples like that. The next part also, we are told that the variation with time of the PD of the smoothed output is shown here, and we are supposed to determine the time constant. Okay, so discharging is happening in this region. This is where discharging is taking place, this region here. This is where discharging is taking place. Then we need to find the time taken for this particular capacitor to discharge from a total voltage of 4, and it just discharges to 3.2. Yeah. Yeah, so you can see now it's discharging to 3.2, and it's falling. The PD is decaying from 4 volts to 3.2. So we can be able to use this in order to work out the time constant. So we shall use the relation that the voltage that's remaining, the voltage that is remaining after the decay is equal to the initial voltage, the original voltage, times the exponent of negative t over RC, whereby RC is the time constant. RC is the time constant in this particular case. So we can now say 3.2 is equal to 4E is to 8. Now in this case, I'm not going to include the microsecond, because I'm working out the time constant also in microsecond. So I'll take the time for the decay to remain 8. millisecond, right? Millisecond, not micro, millisecond. So which means that I'll use the 8, and the 8 is from the 5 to the 13 value that I'm having here, because the discharge is taking a period of 8 milliseconds in this case. So I'm going to say 3.2 is equals to 4 into exponent of -8 over the time constant. Time constant can also be written as tau. RC can be written as tau. Tau means time constant, which is the same as RC. Introduce natural log both sides. Then we are going to simplify, and our final expression is going to be 36 milliseconds in that case. Now, a sinusoidal AC power supply has a maximum power of 16 watts. Now, after full wave rectification, the mean power that remains after rectification, because some power is going to be lost, is going to be a half the original. The original, our P naught is 16. So P power that's remaining after half wave, full wave rectification is going to be a half of the original, which is going to be 8. Then after half wave rectification, for a half wave rectification, it's going to be a half of full wave rectification, and that's going to be a half of 8. That is going to be 4 watts. Guys, if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. Let's look at another question that also was tested in one of the years here. We are told that the figure shows the variation, and if you would like to download this particular PDF I'm having here, check out our Patreon page so that you can be able to download it, because there's a link I've added in the description that is going to take you straight to this PDF so that you can be able to download it and have it with you in the process of you following through this particular video. We are supposed to show that the energy stored in the capacitor is 1.8 millijoules. Yeah. This capacitor C is charged. So when it's fully charged, it's having a total potential difference of 8. So as it is charged, the PD will be decreasing with time as the charge is decreasing with time. So if we are working out the total energy, the energy stored in the capacitor at time t is equals to 0, we are going to work out the area under this graph, which is going to be 450 microcoulombs times a half times the height, which is 8. If we work it out, you are going to get the final answer as that. Determine the capacitance of the capacitor. You can select one of the values from the straight line graph here. You can identify a point and then apply the formula charge is equal to CV so that you can be able to work out the value of that capacitance. Otherwise, you can be able to work out the gradient of this line, and the gradient of this line is going to represent one of the gradients of this line, 1 over, because it's V against Q, so 1 over the gradient is going to give us the capacitance. But if it was Q over V, Q against V, then if you work out the gradient direct, it gives you the capacitance. So that's the difference that you really ought to remember as far as this particular topic is concerned. Now, another interesting question. We are told that the figure shows the variation of negative ln of V over 8 against time. And remember, the way to get this formula we shall start from here. Okay, this is the starting point of this formula. V is equal to V naught E of that. Then if you introduce natural log, because if you divide by V naught is the original voltage when the capacitor is fully charged. Yeah, so if you go ahead and introduce natural log here, we are going to have ln of V naught is equal to negative T over RC, and RC, remember, is the time constant. Once you have that, you can decide to divide both sides by the negative. So you see now where this negative is coming in this particular section, where it's coming from. Yeah, you can see where the negative is coming from. That's the origin of the negative. And also, if you rearrange this, you factor this a little bit out, you'll find this is going to be the y and this is going to be x. Hence we have this kind of graph. Now from this graph, what I need to say from this graph, of course this part is not related to Roman 1. Roman 1, I started working it out here, but the gradient of the graph is going to be 1 over RC. We are going to see where we're going to use that. Now, show that when T is equal to time constant, negative ln of V over 8.0, and remember 8.0 was the voltage it was charged to. That when the capacitor is fully charged, is going to have this particular voltage, and we said V naught is the original voltage, and that is why you can see that 8 well seated here in the place of what? V naught. So once you have that, we can now say if T is tau, and then the equation is going to be what? Negative ln T over T. If T is equal to the time constant, then it means this place you are having T over T, this T is going to be tau, because we are told that T is equal to the time constant, and the time constant is this value that we have here. This is the time constant, and if this is equal to this, then all of this expression is going to reduce to what? 1. Hence that's what they were saying. Determine the value of tau for this particular circuit. So if they are saying that T is equal to, when T is equal to the time constant, this one is equal to 1, so which means if you know this, when this is 1, the time we are going to have on the x-axis is the time constant. If this part here is equals to 1, when this is equals to 1, the time you have is going to be the time constant. So which means we are going to go and read that directly, and you read this value here. So the time constant is going to be equals to 3.2. You can be able to read that directly from the graph. However, you can be able to say time constant is equals to 1 over the gradient. And if you work out this particular gradient, you are going to get the gradient is equals to 2 over 6.4. If you find the gradient of this particular line that we are having here, you are going to get 2 over 6.4. But the gradient represents the reciprocal of the gradient. I said it here. Gradient is equals to the reciprocal of RC. So it means that RC is the reciprocal of what? The gradient. So if you find the reciprocal of the gradient, you are going to get your answer 3.2 seconds as our time constant. Calculate the resistance. Now that you have the time constant and the time constant is 3.2, then RC is R is the resistance, C is the capacitance. Because if you have the capacitance and you have the resistor value, if you multiply them, it will give you the time constant. Time constant. So in this particular question, we're finding R, yet we know the capacitance. And the capacitance, we had worked it out in this particular section here, 5.6. So you can say the answer is going to be 5.7 if you apply that in this particular section. Two capacitors A and B are connected in the circuit as shown there. Capacitor A has a capacitance of C and the capacitor B has capacitance of 3C. State in terms of V and C the expression for the initial charge of A. Initial charge of A. Remember, charge is equal to capacitance times voltage. And since all these capacitors, since this capacitor A is in parallel with the power supply, it will mean it's going to have the same voltage. So the voltage here is going to be the voltage that it will be charged to. So we can say charge of A is going to be capacitance of A, which was C times the voltage, and that becomes our beautiful answer. Initial energy stored in capacitor A. Energy is a half CV squared. So if you work it out, that's exactly what you are going to get. The two-way switch S is now moved to Y. This switch is now moved in such a way that is going to cross in Y like that. So which means that this charge C will be fully charged. When it's fully charged and it's connected to another capacitor which was uncharged, it means charge is going to flow because there is the potential difference between capacitor A and capacitor B are not the same. So charge is going to flow. State and explain what happens to the charge that was initially on the plates of A. So since the potential, this is uncharged, it means charge is going to flow. Charge is going to flow until the potential difference between the two capacitors is the same. So that's what you need to put into consideration. Some charges from the plates of the capacitor A will be transferred to capacitor B because the PD across the capacitors is not the same. And this is going to continue until the charge transfer is going to stop immediately. The PD on this capacitor is equal to the PD on this particular capacitor. Let's look at the next question. Show that the final PD across capacitor B is going to be given by this formula that we are having here. Show that. So remember, when this is closed here, it means we are going to have two capacitors which are parallel, and charge is going to flow from this one to this one. Okay. Now, the first thing that we need to remember, the PD in A, when they are going to be in equilibrium, PD in A is going to be PD in B. Charge on A plus the charge on B, charge is conserved. Charge in A plus the charge in B is going to be equal to the original charge that was there in capacitor A. Remember, capacitor A is the one that was having charge. This one is not, or was not having charge. So charge will flow until the charge, now the charge, final charge on this one and the final charge of this other one, if you add the two charges, you are going to get the charge that was in A. So remember, charge is equal to CV. Yeah? Charge is equal to CV. And charge of capacitor A is going to be the capacitance of A times the voltage or the PD of A plus the capacitance, the final charge in B is going to be the capacitance of B times the final voltage in B. But at that point, VA and VB are going to be what? Are going to be equal. So since this expression is having B, that's why now instead of writing VA, I can write that charge in capacitor A will be equivalent to the capacitance of A, which was C, times the voltage of A. But the voltage of A will be equal to the voltage of B. So that's why I've written this particular voltage here to be voltage of B plus capacitance of final charge in B is going to be the capacitance of B, which was 3C times the voltage of B. So that if I add these two guys, I'm going to get 4C VB. But that will be equal to the initial charge that was in capacitor A. That was what? CV, right? So if you make V be the subject, you are going to get your expression like that. And finally, we have this particular section that's I'm going to mention here. Determine the expression in terms of V and C for the decrease of energy stored in the capacitors as a result of the charge of the change of position. We need to remember that initial charge was the charge in capacitor A, which was a half CV squared. Final charge is going to be what? A half 4C. The final charge we're talking about is for the total charge now. The total charge in the connection. And in that case, the total charge is going to be the total capacitance, a half times the total capacitance times the total PD attained, the final PD on the capacitance, which is going to be V over 4. Remember, we had gotten V over 4 as the PD, final PD on the plates of the capacitance. So the final charge that will be in this case is going to be 1 over 8 CV squared. And then remember, change in charge is going to be final charge minus initial charge. The final charge is 1 over 8 CV squared minus the initial, which was this one here. Then if you subtract, you get negative 3 over 8. The negative is telling us there was a decrease in the charge stored. And since they are asking us decrease, you don't include the negative. And that is exactly what we are going to do. So basically, guys, that's where we are going to stop. If you have gotten value from this particular video, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. And also, if you would like to access our notes, you can be able to check them in our Patreon page, whereby you can be able to access the notes of A-Level Physics for all the topics together with the worksheets involved. So guys, I wish you all the best of luck. For those who are going to have their exams, I wish you the best. And also remember to share this channel to your friends. Encourage them to subscribe and to join Profla. See you in the next tutorial.